Last video, we introduced biological catalysts, which we called enzymes, and we were focusing on what enzymes are, how they work, and why they're so special. The topic of this video is enzyme kinetics, so we're going to talk about what enzyme kinetics are, why they're useful, and how we determine them in the lab experimentally. All right, so let's start off with what are enzyme kinetics. So enzyme kinetics are the study of the rates of reaction for enzyme catalyzed processes. And they're really useful because they provide insight into enzyme function. So we can ask questions like how fast is the reaction? How much does the enzyme accelerate the reaction rate compared to the uncatalyzed reaction? Because remember, enzymes are catalysts. Their job is to make a reaction happen more quickly than it would without the enzyme present, right? And in some cases, they can accelerate the reaction by quite a bit. So we can ask that question. We can also think about how does the reaction occur? So now we're thinking about mechanism. And this is really useful if we have two possibilities for how an enzyme might work, but we're not sure which one, then we can do a kinetics experiment. And if one of those possibilities is not consistent with the kinetics, then we know that that's not how the enzyme is functioning. All right, so it's very useful for ruling out potential mechanisms. We can also ask questions like, how does this enzyme behave when we add an inhibitor? We're going to talk a lot about that on Monday. So the thing about enzymes is that because they are the molecules that are catalyzing all of our biochemical reactions, they make really good drug targets. So you can imagine if you have an enzyme in a bacteria that is catalyzing a really important reaction and you add a compound that shuts that enzyme down, going to stop the enzyme from working, cell can't survive without that process, cell's going to die, you have yourself an antibiotic. Methotrexate's another example. That's an anti-cancer drug that targets a very specific enzyme. So this has a lot of applications in medicine as well. All right, so one of the key ideas with enzyme kinetics is that enzymes are very different. We talked about that. We talked about how there's a lot of different chemistries that they can do, a lot of different functions that they can have, but even though they can be so different in their jobs and in the way that they work, all reaction rates and efficiencies for any enzymes can be quantified. And the way that we do that is with the Michaelis Menten equation. And the Michaelis Menten equation is really nice because of a lot of reasons. One of them is that it relates the initial rate, or we're going to start calling rates velocities here, of the reaction to the maximum velocity possible for the reaction. All right, so when I have this velocity, in physics, velocity is just your change in distance over your change in time. So that looks a lot like our rate expressions that we were writing at the beginning of this unit. So we can think about it. Our rate expressions were change in concentration over change in time. So we're still changing something when we're changing time. So what we're doing is we're just taking our rate, and instead of calling it a rate, we're calling it a velocity. And it's still that same change in something over change in time. All right, we're just changing the name. It's the same idea. All right. So that's what it does mathematically. It's relating the initial velocity to the maximum possible velocity. What else can it do? It's really useful because it can provide insight into the affinity of the enzyme for its substrate. And so what I mean by affinity is when you have a substrate interacting with an enzyme, it's held there by intermolecular forces. These are the same intermolecular forces that we talked about last semester. So that's hydrogen bonds, ionic interactions, London forces, and dipole-dipole. And so affinity is a measure of how strong are these forces between the enzyme and the substrate. So if these forces are strong, the substrate's going to come, it's going to bind to the enzyme, it's going to interact with the enzyme through these forces, and if they're strong, it's going to hold the substrate there, which makes the reaction more likely to happen. If they're weak, the substrate will come, it'll collide with the enzyme, but the forces are weak. So there's a good chance the substrate's just going to fall right back off. So this is really useful for thinking about how likely it is that a reaction is going to happen. If you have strong forces, you have high affinity, you're likely to have a reaction. If you have weaker forces, you have low affinity, less likely for a reaction to occur. Very useful there. Another useful piece of information we can get from this equation is insight into the catalytic efficiency of the enzyme. This is particularly nice because it's considering the affinity piece, so how likely the substrate is to bind, and also how quickly the reaction occurs. So if you think about it, you could have an enzyme that's really good at catalyzing the reaction. It can make the reaction happen very, very quickly, but maybe the substrate doesn't bind as tightly, it falls off a lot, so then you're still not going to have a very efficient enzyme. So it's very important to be thinking about both of these pieces, the affinity and the actual reaction. How quickly is that going to occur? Okay, so that's a bit about why Michaelis Menten. Let's start to think about the Michaelis Menten equation. So to do that, let's set the scene. So we're going to have, initially, before anything happens, free substrate, which we're going to call S, and free enzyme, which we'll call E. All right? And they're going to be moving around in the cell, and eventually they're going to collide with each other. And when that happens, they're going to form this enzyme substrate complex, which we're going to call the ES complex. So enzyme substrate, right? So the enzyme substrate complex is going to form. Once that happens, the actual reaction can happen. So here, we're taking this bond and we're breaking it. And that'll allow us to release these two groups separately, right? So we're bound in the enzyme substrate complex. The reaction occurs. The next thing that happens is that the products, which we're going to call P, will be released from the enzyme, and the enzyme will be regenerated, ready to catalyze another reaction, right? So what's going on here chemically? What are the elementary steps that have to happen during an enzyme catalyzed reaction? You can think about it as there's kind of two stages. So there's two elementary steps. So the first one is the binding. So enzyme and substrate coming together to form the enzyme substrate complex. So that's the first step that has to happen. Then, once the enzyme substrate complex is formed, that decomposes into free enzyme, ready to catalyze again, and the product, right? So these are the elementary steps of the process. And because they're elementary steps, we can use those to get rate laws. Before we do that, it turns out that we can write these as one big chemical equation. So let's do that. Let's write E plus S. Going to give us enzyme substrate complex, which will decompose to enzyme plus product. All right, and each one of these has a K. All right, so what's going on here? Why did I add this double arrow? And what are each of these Ks? So this double arrow is just telling us that the reaction is reversible. All right, so you can have enzyme and substrate come together, form the enzyme substrate complex. That can then go on to produce product, or what we were kind of talking about earlier is that that can fall apart. The substrate can fall off the enzyme without having the reaction occur, and we end up back where we started with enzyme and substrate. So we have to consider that both of these processes can happen, right? So that's why we have that double arrow there, because it's telling us that this first step is reversible. It can go both directions. Now, what are these Ks? So these Ks are each just the rate constant, that same rate constant that we've been talking about for each of these individual processes. So K1 is going to be the rate constant for ES complex formation. So So it's going to go with this reaction. K minus 1. So this is the same step, which is why it's still 1, but it's in the opposite direction, which is why it's negative. So that negative is just letting you know it's going in the opposite direction. That is the rate constant for the reaction, enzyme substrate complex decomposing into enzyme and substrate. All right, so that's that reverse reaction. Same step, opposite direction. K2, now we have a new step, so we get a new number. That's the rate constant for product formation. All right, so that goes with this reaction. Enzyme substrate complex decomposing into enzyme and product. All right, so that's kind of what's going on with this process. So now that we have all of that, we can use Michaelis Menten to actually relate the overall reaction rate to the substrate concentration. So let's go ahead and do that by writing the rate laws, right? So each of these is an elementary step. So we can get the rate law directly from the equation. So let's start with this one. It's a bit more straightforward. So let's call that product formation. And keep this idea in your minds because you're going to need it later. So product formation, the rate law is going to be, let's call it velocity. It's going to be equal to K2 times our reactant concentration, which is enzyme substrate complex. All right, that's just like what we've been doing. So now, let's look at this guy. Formation of enzyme substrate complex. So this is going to be a lot more complicated because each one of these steps is going to affect the concentration of the enzyme substrate complex. So let's write out what that looks like. So formation of ES complex. So because each one of those can affect the concentration of the enzyme substrate complex, we have to consider them all. So velocity is going to be equal to K1 times concentration of enzyme times concentration of substrate minus K minus 1 times the concentration of enzyme substrate complex minus K2 times the concentration of enzyme substrate complex. All right, so what's going on here? So this is the step that makes ES complex. So that's positive because it's making enzyme substrate complex. It's adding to the concentration of enzyme substrate complex. These are depleting the enzyme substrate complex concentration, which means they cause us to lose our enzyme substrate complex. And because they're causing us to lose enzyme substrate complex, they have to be subtracted from our rate of formation of enzyme substrate complex. And that gives us an accurate rate describing how much enzyme substrate complex we have at any given moment. All right, so we have to consider all three of these steps for enzyme substrate complex because they're all affecting its concentration. And the rate is affected by the concentration of whatever you're taking the rate of. All right, so very important to consider all of these. But now we run into a problem. This is very complicated. And so we need to make some assumptions to make that simpler so we can work with it. And the main assumption that we make is that we have a steady state. So what does that mean? So we're going to assume that substrate is present in much higher concentration, high excess compared to the enzyme. So that is basically just saying that the concentration of substrate is much, much greater than the concentration of enzyme. All right, why is that useful? That's useful because when we're in this situation, we have way more substrate than we have enzyme. All of that enzyme is going to be bound to substrate. All right, so all of our enzyme is going to be in the ES complex. What's more is that when we have the reaction occur and the product is released and we have free enzyme again, because we have so much substrate, another substrate molecule is going to be ready and waiting. It's going to bind and pretty much immediately after we release the product. So we're never really going to see us not having all of the enzyme in the enzyme substrate complex for the purposes of these experiments, all right? So our enzyme substrate complex concentration is remaining essentially constant over the time intervals that we're looking at until we start to really deplete the substrate. But everything that we're doing is assuming that we have very high substrate. And this allows us to treat our enzyme substrate complex concentration as constant in our rate equations. Because what we have is that our rate of formation is equal to our rate of consumption. So it's being formed at the same rate that it's being used up. So then our change in concentration is basically going to be 0. All right? Why is that useful? Our velocity is equal to our change in concentration over time. So then if this is 0, it makes the whole rate equal to 0. All right, that's going to be very important. We're going to use that very, very quickly. But before we do that, we have 2 more things to talk about. So the first is that even though enzyme substrate complex concentration is constant, we're still making product and we're still consuming substrate. All right, so substrate concentration is going down, product concentration is going up. So we're starting to have ourselves an experiment. All right, this is constant, but we still have changes in substrate going down, products going up. All right. The other thing that we need to talk about is that because our substrate concentration is so high, we can assume that none of our product is rebinding to the enzyme and forming enzyme substrate complex again. All right. And that's because we're starting with 0. So our initial concentration of product is 0. Even once the reaction starts, there's not going to be a lot of product compared to our substrate. So our substrate concentration is always going to be much greater than our product concentration. So it's always going to be more likely for a substrate molecule to bind to the enzyme than a product molecule to bind to the enzyme. So we can just assume that once product is formed, it stays formed. And that makes things a lot more simple for us. All right, so now let's actually derive this equation. You don't need to be able to do this. I really want to emphasize that. You don't need to be able to do this. But it's good to know where it comes from and kind of how we got it. So we're going to start with our rate equation for enzyme substrate complex formation. But we just said that we're making the steady state assumption. Where change in enzyme substrate complex concentration over change in time is 0, which means our rate is 0. So we can rewrite this as by setting it equal to 0. So I'm just going to rewrite everything here. All right. And so now we're going to get rid of these minus signs. So I'm going to add both of these groups over to the other side. All right, so that's step 1. But now we have a problem because we have some things in here that we can't measure, specifically our free enzyme. Because our substrate concentration is so high, we don't really know what that is, all right? And what we do know is how much enzyme we initially added. So we know our total enzyme concentration because we know how much we added. And we also know that all of our enzyme has to either be free or it has to be an enzyme substrate complex. All right, so our total enzyme is equal to our concentration of our enzyme substrate complex plus our concentration of free enzyme, right? Because the enzyme has to either be unbound or bound. It doesn't have any other options, so the sum of these two together gives us our total enzyme concentration. That allows us to, we're going to rearrange that. So we have free enzyme is equal to the total enzyme concentration minus our enzyme substrate complex. And so now we're going to take this, we're going to substitute this in here. So let's do that. So K minus 1 times enzyme substrate complex plus K2 times enzyme substrate complex. K1 times all of this all right? So now we're just going to do some algebra. We're going to divide. So over here on this side, we are going to pull out our enzyme substrate complex because it is the same, because it's common with both of these terms. And then we're going to divide that over. But I'm going to do that step by step. So enzyme substrate complex times K minus 1 plus K2. That's going to be equal to K1 times all of this. We're going to divide this over. That's going to cancel. Right. So then we have I'm just rewriting what we just did so we can see it. All right, and then we're going to divide that by our K1. So that cancels. And so then we have make sure you're paying attention to your parentheses. That's S over ES concentration. And we're going to call this, we're going to call that Km, which is our Michaelis constant. And that is very useful. We're going to talk about that later. So that is going to all become Km. So another arrow. So now we're going to multiply this over to this side. So multiply both sides by our enzyme substrate complex, so that'll cancel. on the right. And now we want to get this by itself. So the first thing we're going to do for that is we're going to distribute over here. So Km times enzyme substrate complex is equal to total enzyme concentration times substrate concentration minus enzyme substrate complex times substrate concentration. And the reason that we're doing this is because we can't measure enzyme substrate complex either, but that will come into play later. We have to do this first. So now we're going to move this, we're going to add that over here. So right. And then 2 more steps on this slide. So I'm going to change my color and I'm going to bring this up into this spot. All right. So this is going to come up here. So we're pulling out our enzyme substrate complex now because it's common to both things on the left side. Sorry, I'm still getting used to the tablet. Is equal to our total enzyme times our substrate concentration. Now we can divide this by our Km plus substrate concentration. So that cancels. And now we have our enzyme substrate complex concentration by itself. And we're going to use this on the next slide. All right. So that is kind of one of the biggest things because we need to have an equation for this because we can't measure it. You'll see what we're going to do with this on the next slide. So let's go to the next slide. So the way that we do this experiment, one of the tricks that we use is that we use initial velocities to determine these enzyme kinetics, all right? And what an initial velocity is it's measured early in the reaction when we still have most of our substrate left. So at least 90% of our substrate is still present. And then what we're going to do is we're going to measure product formation, right? So the reason why it's important to use the initial velocity is going back to that idea of any potential effects of having product build up. This keeps our product concentration low. So we're not going to have any effects from having product starting to build up. We're going to measure product formation. So we said back at the beginning that our product formation was our K2 times the concentration of enzyme substrate complex, because that is what decays, that's the reactant that forms our product and our free enzyme. All right, so that was our rate of product formation. So if we're using an initial velocity, we can just rewrite that as V sub 0. So V at time 0 is equal to K2 times our enzyme substrate complex concentration. All right, and we're doing this because we're measuring product formation. It's a lot easier to measure something building up from 0 than it is to measure something going down from a very high concentration. So that's why we focus on product formation. And so now we're going to take this. We just said that our enzyme substrate complex concentration is equal to this. So we're going to take this, we're going to substitute that in there. All right, so what we end up with is this. All right? And so that is how we incorporate our initial velocity. So now we have this in terms of things we can measure. We know our total enzyme concentration. We know our substrate concentration. So now we have it. This is a much more useful form of the equation. But let's go back here for a minute, because I promised you at the beginning that we would be relating initial velocity to maximum velocity. All right, so how do we do that? To do that, we need this equation. And we need to think about what's happening when we are at maximum velocity. So at maximum velocity, so at Vmax, all enzyme is in the enzyme substrate complex. So let's think about this. We can't have more reaction than we have enzyme, right? So it'll never go faster than when all of the enzyme is bound to substrate, because the enzyme is the catalyst that's allowing the reaction to occur in the first place. So then at maximum velocity, the enzyme substrate complex concentration is going to equal the total enzyme concentration, because all the enzymes are going to be bound, because that's how you're going to get to your maximum reaction rate, is when all the enzymes are bound, catalyzing reactions constantly. All right. So we can take this and now substitute that into this equation again. So now we can say Vmax is equal to K2 times our total enzyme concentration. And what do we have in our equation here? We have K2 times our total enzyme concentration. So we can rewrite this one more time as V0 equals Vmax times our substrate concentration over our Michaelis constant plus our substrate concentration. And this is the final form of the Michaelis Menten equation, right? And so in the next video, we're going to go over how to interpret this equation, how to use it, and we're going to do some practice problems, all right? So this is the Michaelis Menten equation. Next video is focusing on how to use it, all right? So that is everything that I have. And I will see you in the next video.